As a part of NASA's CLIPS initiative, Blue Ghost Mission 1 will deliver 10 NASA payloads to Mare Crisium, which is in the northeast quadrant of the moon's near side. This mission in particular marks a significant step forward in advancing our lunar research and enabling a sustainable presence on the moon.
Ignition and liftoff. Fairing separation confirmed.
Firefly's Blue Ghost lunar lander was designed for stability. It's about 6.5 feet tall and 11.5 feet wide, so it has a low center of gravity and a wide footprint. Blue Ghost has a robust communication system with 1 X-band antenna and 3 S-band antennas that enable HD video transmission from the lander to Firefly's Mission Operations Center in Texas. The lander has 3 solar panels to help power Blue Ghost and our 10 NASA payloads during transit and on the lunar surface. For propulsion, Blue Ghost has 8 RCS thrusters, or reaction control thrusters, that Firefly designed and built in-house. These thrusters help maintain the lander's orientation during maneuvers and independently perform the final descent by pulsing for a soft landing. We have 12 attitude control system thrusters that help point the spacecraft in the right direction. These are actually the same ACS thrusters we use on our Alpha rocket and Electra orbiting vehicles. Blue Ghost has 1 main engine that provides high thrust for our lunar orbit insertion and braking burn prior to landing. The lander has 4 propellant tanks that carry our hypergolic fuel and oxidizer. We have 2 pressurant tanks that carry our helium. Blue Ghost is equipped with 49 struts that connect our upper and lower panels to provide a rigid structure. These struts were built in-house using the same lightweight carbon composites we use on Firefly's launch vehicles. Blue Ghost has 4 carbon composite legs and foot pads that utilize crushed core honeycomb to absorb shock and stabilize the lander as it touches down on the lunar surface. Our foot pads have contact sensors on the bottom that signal engine shutdown upon landing. We have vision navigation software that supports landing by identifying potential hazards on the moon, such as rocks and craters, before determining the safest landing site.
We have the Next Generation Lunar Retroreflector, or NGLR, which is a passive instrument, meaning it does not power on. Instead, it will beam incoming laser light from Earth back in the same direction. The time it takes for the light to bounce back can be used to calculate the moon's shape and distance from Earth. Another payload on this flight, the Lunar Environment Heliospheric X-ray Imager, or LEXI, will aim to capture the first global images of the magnetic field that shields Earth from solar radiation, providing insight on how space weather impacts us here on Earth. During transit, LEXI operated for more than 50 hours total in preparation for collecting images from the lunar surface. Now let's talk about RAD-PC next. RAD-PC is the radiation-tolerant computer demonstration. You can't send just any computer into space. That harsh environment in space and on the moon can lead to malfunctions, system crashes, and permanent damage. Designed to recover from issues created by radiation, RAD-PC provides a cost-effective solution. Lunar GNSS Receiver Experiment Payload, or LUGRA. We discussed earlier is jointly developed by NASA and the Italian Space Agency. LUGRA is investigating whether Earth-based global navigation satellite systems, or GNSS signals like GPS, can be used for space-based positioning, navigation, and timing from a spacecraft's initial launch to lunar landing. During transit to the moon, LUGRA successfully tracked GNSS signals from GPS and the European Union's Galileo constellations, and broke the record multiple times for the farthest GNSS signal acquisition ever. It's equipped with a drill and a thermal probe which will dig up to a depth of 3 meters into the lunar surface and take some thermal measurements. By making similar measurements at multiple locations on the lunar surface, LISTER could shed light on the geological processes that shaped the moon. Now next up we have the Lunar Planet Vac, which is designed, it's LPV, and it's designed to collect lunar soil samples from the surface using a burst of compressed gas to drive the soil sample into the container, and additional instrumentation will then take images of the container's contents and transmit those results back to Earth. The LPV payload is designed to help test low-cost technologies for collecting and analyzing samples, improving our ability to search for water, helium, and other potential resources on the moon. We learned during the Apollo missions that lunar dust, or regolith, is very challenging to work with. It's extremely abrasive and actually clings to everything: gloves, boots, vehicles, and mechanical equipment. Now, next up, to learn about the potential challenges that dust poses to future Artemis-era missions, the Regolith Adherence Characterization Instrument, or RAC, will measure how lunar dust accumulates on different surfaces and materials. The data captured could help more effectively test, upgrade, and protect spacecraft, spacesuits, habitats, and equipment in preparation for continued exploration of the moon. Magnetotelluric Sounder, or LMS, will probe the interior of the moon to depths of up to 700 miles. Now, that's 2/3 of the way to the lunar center. The measurements will shed light on the differentiation and thermal history of our moon, a cornerstone to understanding the evolution of solid worlds.